Well, hello, and welcome back. This is Beyond Code Live. As I said yesterday, tonight we are talking about recursion. What I want you to know, first of all, is recursion is a normal, everyday thing that you do all the time. So we're going to take a super simple example, and we're going to explain it in English. We're going to turn it into code, and then I'm going to give you kind of a more complex example just as an explainer. First of all, every house has a rule. You must eat all of your food before you play video games. All right, so this is a rule, and we'll just shorten it a little bit. Eat all of your food before playing video games. All right, you're familiar with this. You hated it growing up, you do it to your kids. That's how it is. So step one, what we need to do is define how this is accomplished, but we need to think like a programmer. We need to think logically. And so we need to think first about what the end condition is, because most people will say, well, if you've got your food in front of you, step one is going to be, you're going to take a bite of your food. This is not correct. So it's really important in recursion to understand what the end conditions could be, and if there must be an end condition, or if it's only possible that there's an end condition, meaning that it's possible that there is no end condition. Now here, there is an end condition, which is that if there is no food on the plate, and you didn't feed it to the dog, you've eaten all of your food. So let's just keep it simple and say, check if there's any more food on plate. And then step two would be if no, because we want to think the reverse. If not, go play video games. All right, done. If there's no more food on the plate, I can go play video games. So what's step three then? Step three means there is food on the plate, so what I need to do, I need to take a bite. And then step four would be what? Take another bite? No. We need to go back to step one. This is kind of what recursion is. This could be recursion or a loop, and I'll explain the difference. But essentially, go to step one. Now, if we want to make this more like recursion, let's actually say go to rule. And we could say that all of these are nested under the rule. So this kind of feels like recursion, and we're going to translate this into code, but this is something that you intuitively understand. You've got some sort of task, there's an end condition, and you're going to go back to the start and start from the beginning moving forward if the condition wasn't met. And the last, this is the part that's recursion, is that the last piece that you do, if you manage to get to the last piece is you go do the thing again, right? So we'll turn this into a function. So the function is finish food, and the function is going to receive, we're going to say bytes. It's the number of bytes that are left, okay? And so let's go ahead and just say that the number of bytes that are going to be on the plate, if you could quantify them that way, is going to be 10 bytes, all right? Let's just say that. Now I can get rid of that. So what's step one is check if there's any more food on the plate. So if the number of bytes is 0, because we want to think about the end condition, then we know that there is no more food on the plate. So if that's the case, we can return true. That means we get to go play video games, all right? So it's the first thing we want to think about is how do we exit? Just very common in programming, think about exit conditions, error conditions, finishing conditions. That's generally the first thing that you want to check in a function or a loop or what have you. Now the next bit is to take a bite. So in this case, taking a bite is going to be represented as just subtracting 1 from the bytes. So that's good. And then our final step was to go to the rule. So if we want to evaluate this again, we call the same function that we're already in. This is one of the telltale signs of recursion rather than a loop, is that within the function, you call the function, right? So if we were to let this program play out, it's going to, every time you call a function, it creates a copy of that function. So if we call this function 10 times, we have 10 different copies of that function, which is, we're actually going to have 11 different copies here. So first, we have the copy of the function that has 10 bytes. And it comes in and it checks, is 0 equal to the number of bytes? It is not, so we are going to skip this part. Then we're going to take a byte, which maybe I should even label that, take a byte. And then once we've taken a byte, we're going to restart back at the beginning. But with the new updated information. So bytes, since we took a byte away, bytes was 10, now it's 9. And then we're going to go through this again. And then bytes is going to be 8, and we're going to go through it. All the while, we had a copy that has 10 bytes, a copy that has 9 bytes, a copy that's 8 bytes, so on and so forth. So we get down, let's say there's 1 byte left. We're checking. It's not 0, so we're going to take a byte. Now we're at 0 bytes. Now we're going to return finish food, which means that we're passing in 0 bytes, and we check this out, and this returns true. Now this is important. This is important to understand about recursion. We now have 11 copies of this function, and we just got to squish one of them, which is the one that had 0. That was the 11th. So it's returning true. Now every other copy of the function is in its execution is basically here at line 11. It's waiting for it to be able to return the result of finished food. And there hasn't been a result because it's been creating copies to find that result. So now what's going to happen is the true is going to get returned, and then we're going to go back up the stack. And so now this one gets squashed, and this one gets squashed, squash, 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 boom. The end result, we could say return this, finished, it's going to be true. Get to play video games. And that's going to be true because this is a very simple program that only has one possible outcome, which is that we eat all of our food. It's the rule. We must obey. So the bits of this that make it recursion are that we're passing in pretty much all the information that the function needs as its state. This is a very simple example. There's only one thing, and it's a number. But there might be multiple things that we would be passing in, like, I don't know, maybe bytes of vegetables, bytes of fruit, so on. In this case, we just have bytes, but there might be multiple things that need to be passed in. And then the other bit is that at some point in the function, we have the option of calling the function again, or in more complex cases, which we'll see in a minute, we might be calling a function that ends up calling this same function. But proper recursion is often associated with the function immediately calls itself. Okay, now, from this point, let's take a look at what this might look like as a loop rather than recursion. So very simply, the difference is that we have to manage more of our own memory and state. That gives us the advantage that we can actually, in some cases, be more efficient, but it is also more burden that we take on. You won't really notice much in this example, but I'll show another example later where it perhaps will kind of click better. But so now we have the number of bytes as 10. We'll just write a while loop. So we'll say while 0 is not the number of bytes, meaning while we still have more food to eat, and we don't need that condition anymore, we're going to take a byte, and then we don't need to return because that would take us out of the while loop, and we don't need to call any function because everything that needs to be done can be done in this. So let's get rid of that. Now all we have is while essentially there are still bytes, while bytes are not, while the number of bytes isn't 0, subtract one of the bytes, and then we continue. So in terms of what it accomplishes, it looks very similar. And in this case, because it's a very simple case, it looks entirely simpler because managing the number of bytes is not hard. Now we only have one copy rather than 11 copies of this, and we don't have any copies of any other information that might be in the function. So it seems like we're better off. And then at the end, we could just log out true here, and now we've converted that from recursion to a loop. Almost depending on things like asynchronous programming and whatnot, but put that aside, all loops can be represented as recursion, all recursion can be represented as loops. There's just cases where it might be easier or not. Now there's one caveat that I want to put in here, which is recursion can be just as efficient as loops. When it is, that's called proper tail recursion. So let me go back here and we'll take a look at this function as it was here. Now, proper tail recursion is when the program platform can determine the last thing that's done here, or one of the exit conditions is finish food, and it can determine that it is safe to, instead of making multiple copies of the function in the stack on top of each other, the stack is the area of memory in the computer, in a computer program that is allocated for making copies of functions. So if it can determine that it is safe, then it will just replace the function on top of itself and overwrite that copy of the function, so you end up only having one copy of the function rather than 11. And that, again, that's called proper tail recursion. In that case, the recursive version and the loop version are theoretically equally efficient. So that aside, having gone over both, let me introduce why you might want to use recursion, because that example makes it seem like we would just always want to use loops no matter what, because it looks simpler and there's no efficiency gains in recursion. So let's consider a maze, okay? So think in your mind a maze, and we're going to consider a very simple maze that does not have any loops in it, which is like most of the mazes you get in your crossword puzzle book or whatever, right? So you can go into the maze at one point, you can exit the maze. At another point, your job is to find that, but we're not going to have any places in this maze where it's possible that if you were to take a turn, you could end back up on a place where you had already visited before. This is going to be a maze where there's only dead ends and there's no loops, okay? So this is a lot easier for a person to think about. Essentially, if you were physically in a maze and you wanted to keep track of everything, you could just walk the entire maze and then you could always turn right. Anytime there's a choice, you could always turn right. And if it's the type of simple maze I've described, then you would never encounter or you would always encounter the exit. It might not be the most efficient path, but if you just kept your hand on the wall and just you kept your right hand on the wall and just walked, and always kept your right hand on the wall, you would exit the maze, if it's that simple type of maze. So if you are writing a function that mimics what you do in real life, this is very simple. So we have this function that is finish maze, and it's going to take in a position. We're going to assume this maze has no loops. So what we're going to do first is, and I don't have these other functions defined, but you can imagine that they exist and they check the value of the position and can tell you these things if we had that other information available. For simplicity, we'll go with this. So the first thing we want to check is, what's the exit condition? Well, are we at the exit of the maze? So we're given a position that we're at in the maze. We check to see, is this position the exit? If so, we return true. We've completed the maze, okay? Now, the next thing that we want to check is, can I go, before I said right, so let's switch this up and say that right is what we're checking, okay? So I want to know, can I go right? And I pass in that position, and it's going to do some sort of checking with where the walls are in the maze and where my position is, and is it possible that the next step I take is to go right? And if so, then it's going to say, finish the maze, go right position. So go right, calling go right on position is going to give us a new position that's updated that is one more position to the right, and then that's going to be called into finish maze, and then we're going to continue. So this is a more complex recursive function, but it's a lot simpler to reason about, at least for me, than the equivalent loop function of this. And so then we go through, what will eventually happen is, if this line right here ends up being the exit of the maze, then it will return true, and then we'll back out. If that next move is not the exit of the maze, but there's another way to go, then we're back at the top of this function. It's going to check, can I go right? Let's say no, it can't. So it's going to check, can I go straight? No, I can't go straight. Can I go left? Yes, I can go left. Okay, it's going to go into that function. Now it's going to be back at the top of the finished maze with the new updated position that's been at the left. And then, it goes on so on and so forth until it either finds an end and then it backs out, or until it finds, it finds an end one way or the other. Either it finds a dead end or it finds the end of the maze. Now, what's nice about this is, notice that I wouldn't have to be keeping track of much information here. Like, there's a new copy of the position for every function, for every copy of the function that's been called. So the stack is going to grow, and the stack is fast memory, so we don't necessarily need to worry about that as long as the number of possible permutations of the maze is not larger than what the stack is, which that's a technical detail we won't go into here. But in this case, it's pretty easy, at least for me, to reason about this code and understand what it's doing. If we were going to do the loop equivalent of this, we would be keeping track of more information. Importantly, because a maze has multiple options and the paths tree out with branches, if you were to do this in a loop, you would have to keep track of that path and be adding and subtracting to it over and over and over again by yourself. Essentially, it's going to look similar, but it's not going to feel as clean, perhaps. Like, it's not, I don't know. It depends on the person, but to me, it just doesn't feel as fluid and nice. So that's what recursion is. That's how it's different from a loop, and when you might find it more natural to use. And again, the big gotchas are, you need to be really clear, just as with all loops, because it is a type of loop, what your exit conditions are and making sure you're checking those. Otherwise, you end up with something that goes on and on and on and on forever. For example, we could create a function. This is the canonical example that's like kind of the meme for what goes on in an interview. That is the Fibonacci sequence. And the Fibonacci sequence is, you take the two previous numbers, you add them together and use one of the last of the previous numbers with the new number you created. So 1, 1, 2, 3, 5, 8, 12, no, 13. I don't even know if I'm doing it right, but it's the shape of the Eiffel Tower is based on that mathematical function. That mathematical function has no end. It can go on forever. So you have to define how many of numbers in the sequence you want. If you were to just call that recursively, or if you were to do it in a loop, whatever, it'll go on and on forever. So you just need to be careful of that. Anyway, I hope that is helpful in understanding what recursion is. Please let me know any questions you had about this, any criticisms about something that was not clear or made it more confusing. I'd love to address that as an addendum to this. Also, you can subscribe on YouTube and Facebook. This is Beyond Code Bootcamp. And I also do, if you're interested in some lifestyle type stuff, I'm also doing health, wealth, and commitment. And you can find links to all of that stuff in the description or the comments here below. Thanks for watching. Thank you especially if you left any comments or likes or questions. And I will catch you, except not because the whole, camera thing, I can't actually see it. But I look forward to the interactions next time. You have the best night ever. Adios.